Right, so let's talk about the new age of weather and climate computing. And as you can imagine, it has to do with HPC, it has to do with machine learning. I'm going to walk you through that sequence and want to acknowledge a couple of people from my former employer, the European Center for Medium Range Weather Forecasts, and of course, Thorsten Höfler before. I should also always thank Thomas Schultes, actually, because he's like my HPC brain. And I think we started working together maybe 10 years ago, more or less. And it's been an inspiration for me, I have to say. So, first I want to convince you of the power of numerical weather prediction, apart from feeding your app that you're asking every day what to do the next day or the weekend. You may remember this picture. This was taken on board Apollo 11 in 1969, and it shows Earth, the blue marble, very famous. And this is how it can be recreated by a numerical weather prediction model with only being tied to the observations that were available at that day. So no satellites, a few ships maybe, a few buoys, some land observation stations, nothing in the southern hemisphere. And yet you can see that the numerical model is actually able, with these anchor points, to recreate almost exactly that image. There's differences, but there's also very good commonalities. And that shows you how powerful this mechanism is of combining a numerical simulation model that's very realistic, anchored by observations that show the real world, to reproduce what we conceive what we perceive as weather. Today, we're here. You know, you have a left and right image, and one is a satellite observation, and the other is a numerical simulation of the same time, the same date, and the same disk of the Earth. And we're not going to do a vote on what is what. I'm going to tell you the left is the satellite and the right is the simulation. So between the old days, 1970s, when numerical weather prediction started to become operational, and today, we've done fundamental leaps towards much better predictions, a much more realistic representation of the entire Earth system processes, so not just clouds, but also land surfaces, oceans, snow and ice, to create something like this. Apart from great science, what's also interesting and important to understand is that global weather prediction is an enterprise. We have a very well-organized scientific community, but also a very well-organized community that furnishes us with observations. We received, or I say we, ECMWF, receive per day about 100 million observations to do what I said before. And we have translated that, plus a better understanding of the physics, better computers, I'm going to come to that, into improved skill over time. And this shows you a time series of skill metric, doesn't matter which one it is, but it shows you that all these curves, which represent that skill, provided by different weather prediction centers that do that every day, over time improves about by a day, a decade. That means, like, you know, decades ago, the five-day forecast is as good as the six-day forecast today. The other interesting aspect of this is that the top two curves, the red and the blue, are European centers. So we actually have European leadership in that domain in global weather prediction. And it's been like this, you know, as far as you can see, these curves go back. So we have a very, very large, important heritage, actually, of intellectual property and scientific knowledge in Europe to do that. That's very interesting. So part of that weather enterprise is the World Meteorological Organization, funded by the United Nations and others. And what you mostly see of weather anyway is TV news, a couple of minutes or a minute, what you take from the internet or the radio, if you're still listening to radio. But what sits below, what you can't see, is actually a huge intergovernmental and very large, in terms of monetary terms, investment in national services, how they talk to each other, free exchange of data. I'm sure we're going to talk about open data later, into weather models, space, aviation, marine services, how to issue warnings, what are the standards actually for warnings, who has the responsibility and the rights to issue a warning, then how to translate this into local services for flooding, for example, pollution, these kind of things. And as I mentioned, this incredible exchange on observing systems. All the satellites for Earth observations are actually coordinated between the space agencies in the world. That's quite an achievement. So extremely well-developed operational community, joint research strategies, jointly investing in observing infrastructures, collectively providing services. And I think that's a great achievement. But of course, we all care about daily weather, but we care even more about future weather with climate change. What you see here on the left is different realizations or scenarios of global warming, and you can see the top one that's in red there, how the Earth is becoming warmer if you apply more carbon dioxide to the atmosphere. This is something that international research organizations calculate with climate models, and they create these scenarios, and you know from the press that we want to stay below the 1.5 degree scenario, which is the second column from the left. And then you can see, if you play through these scenarios, what global warming means regionally, but also what it means, for example, to soil moisture, droughts, wildfires depend on that, and precipitation. And we're much more certain about the temperature change actually than about the others. So we know the climate models agree on certain things like warming quite well, but they disagree on many other things that we need to explore. And we heard already before in Torsten's talk about the need to really drive and push our models much harder than in the past to resolve that gap. And then, something like this, temperature, rainfall, soil moisture, translates into something that means something for society. This is just a figure that NOAA puts together. It's the disasters, natural disasters or weather disasters, whose cost exceeded 1 billion. So there's a lot of others, but those are the ones exceeding 1 billion in 2023. Regardless of climate change, you want to predict those well, because that means evacuation, it means insurance, it means a lot of things for many people. So it's really important to get that right, and how that's going to change in 2050, for example. And we stare a lot at developed countries, but how about those that are not so well developed? For those, climate change and weather extremes matter as well. And if you look at some countries in Africa, for example, compared to Norway, in terms of readiness and vulnerability, a lot of them sit in the top left, so they are very vulnerable and not ready at all. And they need services of an entirely different kind. They can't run expensive models, but they need services. And I'm sure you've seen this a few weeks ago, some extreme rainfall, in our case, means a couple of buildings and bridges go. In other countries, it's hundreds of thousands of people who suffer or die. So in our discipline, computing has always been key. This is a time series of the European Center for Medium-Range Weather Forecasts computing systems over time. And you see that's a log scale, how the sustained performance increases over time. That follows pretty much, not exactly, but follows pretty much Moore's law. So we were able to buy, for kind of the same money or a bit more, computers that gave us an exponential growth. And the blue line on top tells you how we were able to improve our model resolution. And again, Torsten and Thomas alluded to this, how important spatial resolution is to get the details right that matter for local forecasts, but also matter for the large scales. So the leading weather centers right now run machines, kind of 40 plus petaflops, that's not bad. They need that almost all the time. So the reliability requirement is very high, and they're always full. If you buy the next bigger machine, that's bigger by a factor of 5, a month later it's full. I mentioned the 100 million observations per day, and we produce these days roughly half a petabyte per day output that needs to be on the fly post-processed and disseminated to users within hours. So it's all time critical. Ironically, if we look at that same time series of different machines that we had at the center, you see that the sustained performance that we achieve with our weather model has degraded and is down to 4% these days. So we buy a very important, a very big machine that looks very good on the top 500, but what we can actually squeeze out of it with our complex models is only a small fraction. That's a big problem for us. A while ago, Thomas led a paper to think along this leap of resolution and better models that we need to make an important step in increasing our predictive skill. And that paper made an extrapolation based on existing runs that we did with existing models. One is actually a model that was operated in Switzerland not too long ago, and another is the European Centers model. And we made a calculation based on these runs, based on an extrapolation of what kind of machine we would need to really run with a throughput we need to do predictions in real time, nearly real time. And we came up with this number. And I don't think it's too far away from what you introduced earlier in your talk. Still, we did this 3 years ago. So there's clearly something where we have to invest in larger machines. And I think both Thomas and Thorsten made that point earlier. We put a number to this. But it's not just a bigger machine, it's also better computing. I mentioned the 4% of sustained performance that we get. And we look then at different aspects of our problem. Some of these facets of the aspects are scientific, some are more technological. So you want to have time and energy to solution optimized because you want to be quick. You want to port your code from one machine to another. You want to have resilience. I mentioned the 99%. We want to have spatial resolution. We want to add more processes because Earth is complex. And we want to run ensembles for uncertainty estimates. And then we did an estimate, if we invested in everything that's in the box there, how would that score, or how much would that drive us into the right direction? And we came up with that graph. And we also had machine learning on our list, but I think what we put there in terms of expectation was super naive. And that was only 3 years ago. In the meantime, we invested a lot in the other problems, in numerical models, in programming, in heterogeneous technologies, data, I/O, memory, processes, parallelization, you name it. And we've started this more than 10 years ago, and these are just logos of projects we engaged in, all of which are actually funded by the European Commission. And it just shows you that we try to do our homework. We really invested in research to get that right and get that 4% number up, and for the envelopes and budgets that we have, create faster and better predictions, which led us now to a project that's also funded by the European Commission called Destination Earth, that's trying to put this all into a gigantic information system. I'm going to mention that a bit later again. But it also goes now more and more into the machine learning direction. So the weather generator is a foundation model proposal in which a couple of weather centers have invested, and I'm very happy to say that Switzerland is part of that, despite not being part of the European Commission. But many of these projects have been with Swiss partners, and so I think the link between climate science and computational science or computing science is driven to a large degree in Europe by Switzerland. And we also have had a lot of participation with vendors, actually. NVIDIA is one of them. So ultimately, we need more resources and bigger computers, though this is, again, Thorsten's view graph from before. So with weather, we sit slightly above the climate point because we need ensembles. We need to run multiple instances of the model to estimate uncertainty. So our challenge is even larger. And we need bigger machines, which means even more expensive. So that's very clear. So machine learning. I don't have the time to give much information on that pub event with Peter Messmer up there, but that was kind of the start where we at ECMWF thought we should invest in machine learning. That was only 5-6 years ago. And we wrote a paper with more simplified models to understand whether machine learning, replacing an entire numerical methods-driven model with a machine learning network could actually create forecasts that are anywhere near realistic. And we were, at that time, that's underlined in red, quite pessimistic about it. A few years later, we see this. This is an evaluation run by Google. It's called WeatherBench 2. And it's a so-called scorecard. It shows you for different parameters like lead time, so forecast days 1 to 10, of different prediction systems in the rows, and the red ones are machine learning systems. And when it's blue, it means that they beat the numerical systems. So this is where we are today. We have a lot of them, and they look like they beat, the crap out of numerical models, actually. So in terms of performance, they're amazing, and they do this in seconds to minutes. So if well-trained, we now know, coming from the left side, that today we can actually really run forecasts in minutes that have the reliability of what we used to do with numerical models. And that changes the entire sphere, entire weather enterprise that I mentioned earlier. We now have commercial players that tend to be fast, they're agile, they have, from our perspective, unlimited resources, and they have actually a business model. We come with other qualities, but that we need to rethink about actually who owns what or should own what, and where should we really collaborate to make this work. Not only be fast and efficient or effective, but also where we can actually really make data open, where we can democratize science and something like weather, with enormous societal impacts. Which brings us to something like this I've been thinking about for a while, which goes a bit into the direction of what Thomas said earlier, you know, and it shows like a collaboration between, or how a future collaboration between operational weather prediction centers, which is like the top left third, HPC centers like CSCS, and space agencies that provide observational data could look like. And it is probably too cumbersome to explain, but one main change to what we have today would be that a lot of the expensive runs that we presently do in numerical weather prediction will not be affordable anymore to do at home. We buy our own machines usually, but that they will be done by places like CSCS or CSC in Finland. And if you map that onto what we have already, we're already halfway or 50% into this, towards an infrastructure agreement like this. So you could map what we have at the bottom onto CSCS and CSC. You have companies like HP, NVIDIA. Thomas mentioned the long collaboration with NVIDIA on this, for example. We have our project Destination Earth there, and weather centers like ECMWF and Meteorology. Destination Earth, briefly, is a very large flagship program by the Commission. I mentioned it is an infrastructure project, but it is about creating better simulations, so better quality of predictions, but also making the information a lot more accessible and interactive. And that's created alongside your HPC centers, so very large computers in Europe in this case, where we created what we call a data bridge in red. That is your machine learning universe as opposed to the HPC universe. This is very data-rich, very high-speed data connections to the HPC center and interconnectivity with other centers. And only with an interactive space where users can play, having almost, again, unlimited resources, you can serve the service domains like, you know, how to deal with future extremes, energy, traffic, food, water, health. So a lot of what I'm imagining in this infrastructure thinking is already being prepared at European level, and certainly Switzerland is contributing to this. And only then you can deal with extremes at the local scales. You can deal with, you know, preparing the energy markets and where to place renewable energy sources in the future, how to deal with future heat waves, and understand actually what an extreme means in 2040 as opposed to today. So click through this summary. I think we have a very well organized community. We have experience with HPC, but we had a lot of help as well, which is good. Machine learning offers acceleration, but also, as we've learned, full emulation of predictions. And it helps us also to specialize output for specific industries more and more. I think that's a great asset. And in terms of what leads us to CSCS, we may not lead the hardware game, but we lead the application game. And I showed you the skill at the beginning. We have enormous investments, so I don't think it's a shortage of money that gets us there. I think it's all about governance. And in this case, Switzerland actually has a leadership in that link between computational science and weather. And I think CSCS and ALPS will demonstrate a lot of things that actually move us towards that new universe and that new weather and climate enterprise. Thanks very much.